Hello. In this video, Derivative Rules Part 3, we're going to investigate this problem that was posed at the end of the last video, the derivative of x times e to the x. Now again, I told you to make a prediction, and perhaps you thought the derivative of this would be equal to maybe 1, because the derivative of x is 1, and e to the x, because the derivative of e to the x is e to the x. Sort of like saying the derivative of a product is the product of the derivatives, because that's how limits worked. And maybe that's true, but what we should do, of course, is do an investigation. Try to find an argument or a proof for this, because it's not good enough to just take a guess. We need to see if this actually works. So if we do the limit as h approaches 0, x plus h, e to the x plus h, minus x e to the x over h. Well, we can go ahead and do a few things. Of course, we could expand this with a little bit of FOIL. So that's a good first step. We'll get the limit h approaches 0 of x e to the x plus h e to the x plus h minus x e to the x over h. Now, I want to expand these little e to the x plus h's because these are going to be e to the x times e to the h using exponent rules. So we can go ahead and write that as the limit h approaches 0 of x e to the x e to the h plus h e to the x e to the h minus x e to the x over h. Now, if you notice, we can actually begin to group some of these together. There's going to be an e to the x we can group. There's going to be some e to the h's. So we can look at factoring and rearranging and potentially finding some terms in common. Not between everything necessarily. I guess there is an e to the x in common, so we could take that out of everything. So we'll get the limit h approaches 0 of e to the x, and then we'd have x e to the h plus h e to the h minus x all over h. Remember, e to the x is actually a constant with respect to h, so this can come all the way out of the limit. We can take this all the way out. And now I'm going to look, there's an x and there's an x, so I'm going to put those next to each other and factor those out. So e to the x is out front, limit h approaches 0. I've got x e to the h minus x plus h e to the h over h. So we'll keep on going. Factor out that x. So e to the x, limit h approaches 0, x e to the h minus 1 plus h e to the h over h. Remember, one of the rules with fractions is we can split it up. So we've got one term here with addition, so we could put it both over h. So let's give that a whirl, see if that helps us in the right direction. Limit h approaches 0, x e to the h minus 1 over h plus h e to the h over h. Now the nice thing about that, of course, is the h's can cancel over here. And, well, we're almost there. We know that the limit of a sum will be the sum of the limits, so we could split these up. So we've got e to the x, limit h approaches 0 of x. And really that x, it's not as important. I could put e to the h minus 1 over h. I could kind of put it like times this. We could put it just over h there. It's still the same because it's multiplication. Plus the limit h approaches 0 of e to the h, and I should really put big brackets because e to the x is multiplying the whole thing. Well, I think we're good to go now. This limit here, e to the h minus 1 over h as h goes to 0, this is a special limit. We looked in the last video. This always gives us 1. Here we can plug in h approaching 0. This will be e to the 0, which we can evaluate. And so let's go ahead and plug everything in. This will give us e to the x times limit of x is just x because it's a constant, times 1, plus e to the 0. So that gives us e to the x plus 1, which we could expand as x e to the x plus e to the x. This looks a little bit confusing, a little strange. I'm going to actually write it in the other order. I'm going to write it as e to the x plus x e to the x, just because it'll help us see some of the structure later on. But this is not what we had predicted. If you look back at our prediction, we thought it was going to be 1 times e to the x. And indeed, there is an element of that. If you look here, you could think about there being a 1 in front. So there is a 1 e to the x. But there's also this extra x e to the x business. And so this is clearly not what we were predicting. This is not what we thought the rule was going to be. So we know for sure that it is not going to be just the product of the derivatives. We don't know what it's going to be because this looks strange, but we know it's not that. Now, what we should do is look at another example. So here we have another one. We have the derivative of these two polynomials multiplied. And again, I encourage you, pause the video here and see if you can figure out the derivative. Don't use limits on this one. Just go ahead and multiply everything out. You can actually FOIL both of those and expand it all, and then take the derivative term by term. See what you get as your derivative. Go ahead and pause the video and give it a try. All right, so hopefully you gave it a try. To do this derivative by hand, we're going to go ahead and multiply everything. So we're going to take 3x squared and times it by 4x squared to give us 12x to the 4. Then 3x squared times 6x will be 18x cubed. And so on and so forth. We get 9x squared. Then we take the 2x, so 8x cubed plus 12x squared plus 6x. Then we take the 1, 4x squared plus 6x plus 3. Now we can go ahead and just do the derivative of each one of those. So we just do term by term. The first one will give us 48x cubed. Then we'll get 18 times 3, so 54x squared, 18x, 24x squared, 24x, 6, 8x, and 6. So we can combine some of those terms. We have a 48x cubed plus, well, the 54 and the 24 combine to give us 78x squared. The 18, the 24, and the 8 all combine to give us 50x, and then 12. Now, you're welcome to go ahead and try doing the derivative of this one times the derivative of this one, but it's not going to work, and I'll show you why. If we do the derivative of this first portion here, we're going to get 6x plus 2. If we do the derivative of the second portion, we're going to get 8x plus 6. And if we were to just multiply these two straight away, well, 8x and 6x is only going to give you 48x squared, and we need 48x cubed. So clearly this is not going to give us this. So it's clearly not what we have thought. And so this is important. We'll make a note. If I have, let's say, the derivative of x e to the x, it is not equal to the derivative of x times the derivative of e to the x. That is not a rule for doing multiplication, for doing products. But is there something else we could do? And looking at this here, and looking at this one here, if you spend some time looking at it, you spend some time thinking, you might be able to come up with an idea, with a rule, with a pattern. And I'll encourage you, go ahead and pause the video. Look at how you could combine maybe this and this and this and this. Is there a way you could somehow find a way to do this to get your final answer? So pause the video and think about it for a bit. Is there a rule for doing products? All right, well, I'm going to show you the rule for doing products. So if you haven't thought about it, well, I'm apologizing here, a bit of a spoiler alert. We're going to do how you find the derivative with a product. And here's what we do. You take this portion here, and you do a derivative. So you get 6x plus 2. But then instead of multiplying by the derivative of the other portion, you just leave it alone. Then you put a plus. You take that first term, and because you did the derivative of it last time, you just write it normal this time. So 3x squared plus 2x plus 1. And then you do the derivative of that second term, 8x plus 6. Now you might think I'm totally bonkers with this idea, but let's go ahead and expand this. If we get the same thing we have up here, well, it's got to be correct because it gives us the same answer. Let's see what we get. Well, 6x times 4x squared is going to be 24x cubed. Then we get 36x squared plus 18x plus 8x squared plus 12x plus 6. So that's expanding the first portion. Then we can go ahead and expand the second portion here. So I'll do this in another color. Plus 24x cubed plus 18x squared plus 16x squared plus 12x plus 8x plus 6. Now let's see if we can have any simplification. Well, there's a 24x cubed and a 24x cubed, which will give me 48x cubed. There's an 18x squared, a 36x squared, an 8x squared, and a 16x squared. So if we add all that together, sure enough, we get 78x squared. Next up, we've got an 18x, we've got a 12x, that's 30. Then we've got a 12x and an 8x, that's 20. 20 and 30 make 50. And we've got a 6 and a 6, which make 12. Well, look at that. Right here, we have the same thing as there, which means our rule must be correct. We got the same thing both times, so it must be the correct way of doing derivatives of multiplication. So let's see if it works on our x e to the x. So the derivative of x e to the x. The derivative of the first part would be 1, and then we leave the second part alone. Then we leave the first part alone, we do the derivative of the second part. The derivative of e to the x is just e to the x. And so we get e to the x plus x e to the x, which is identical to what we found using all of our hard work with the limits. And so the question we have, of course, is what is this shortcut? What is this rule? Is there a shortcut to both of these? And the answer is yes. If we were to do the derivative of fx times gx, we would take first the derivative of fx, multiply by gx. This would be all on its own. Then we would add, and we would do just fx, and then times the derivative of gx. And this would be on its own. And those would be our formula. That would work for doing the derivative whenever you're going to have to find any kind of function where you have two functions that are being multiplied together. You go ahead and use this rule called the product rule. Now let's go ahead and practice this rule on a few derivatives. So here I have 6 derivatives for us to practice on. Please pause the video and give these a try, and then I'm going to work through them, and hopefully you're getting the same answer as me. Don't use any limits or any expanding. We're just going to practice this rule. So hopefully you gave it a try, and let's do the first one here. So derivative of x is 1 times e to the x plus x, derivative of e to the x is e to the x. Derivative of 3x squared is 6x times 4x cubed. Leave the first one alone. Derivative of 4x cubed is 12x squared. Derivative of x squared plus 4 is going to be simply 2x times 3x plus 7 plus x squared plus 4 times 3. Derivative of 3x plus 1 is 3, 5x minus 2, plus 3x plus 1, derivative of 5x minus 2 is 5. Again, because the derivative of constant is just 0. Here we go, another one. We'll get 2x plus 1 times e to the x plus x squared plus x e to the x. Here we'll get 2.1 x to the 1.1 plus 7 times 6 e to the x plus x to the 2.1 plus 7x times the derivative of 6 e to the x. That 6 is just a constant, so it comes out and we do e to the x. So hopefully you got the same answers as me on these. Again, we're just practicing our rule, making sure that we can use it properly. So here we have the full statement. Rule 6, the product rule. If f and g are differentiable functions, then the derivative of f times g is the derivative of f times g plus f times derivative of g. The only thing is we haven't technically proved this, because what we've done is we've shown some evidence with 2 examples, and then we practiced the rule, but we only showed it on a couple functions. How do we know this rule is true? Maybe we got lucky. I don't think we did. This seems like the proper rule, but we still should provide a proof for it. We still should make sure that this rule is indeed true. Now, we're going to go ahead and do the proof, and it's just like all of our limit proofs. We start with the definition of the derivative, which comes from the limit, and then we work it through. So we're doing the derivative of fx gx. And so to do that, well, we need to have a limit. Limit h approaches 0 of fx plus h gx plus h minus fx gx all over h. Now, we're going to need a slight technicality as we go through this proof, so I'm going to just mention something here before we get too far in. We're going to have a little note, and so this is part of the proof here. Maybe I'll put it right here. Note, since gx is differentiable, this implies that gx is continuous. Remember, if something is differentiable, then it's automatically continuous. And so at some point in this proof, we're going to encounter the following limit. The limit is h approaches 0 of g of x plus h. And because it's continuous, we're allowed to just plug it in and get g of x. So that's just a technicality that we're going to need in the proof, but we should state it so that we can use it later on. So back to our proof. We have this limit, and we would like to find some way to factor things and cancel stuff or be able to rewrite it, and unfortunately there just doesn't look like anything in common here. These are fx plus h and gx plus h. These are fx and gx. There's really nothing I can factor or work with. So what I need to do is, again, like many proofs, apply some type of insight, some type of technique or trick, if you will. And on this one, it's going to be the add and subtract technique. So we've got this set up, but we have to add and subtract something. In particular, I'm going to add and subtract f of x times g of x plus h. So f of x, g of x plus h, I'm going to add it, and then of course to keep everything balanced, I'm also going to subtract it. And this is still going to be all over h. Now the reason I do that, and you'll see in a moment, is it allows me a little bit of flexibility. This term here is going to have a gx plus h, and so will this term. And these terms in the middle are going to have, well, an f of x and an f of x in common. So there'll be a bit of group factoring that we can do. So let's go ahead and take this term and write it next to the first term. So we'll have the following. The limit h approaches 0 of fx plus h gx plus h minus fx gx plus h plus, I'm just going to rewrite those other terms in the middle in reverse order. So plus fx gx plus h minus fx gx all over h. So let's look here. There's a gx plus h in common in the first, and we're going to go ahead and factor those out of the first two terms. Here there's an fx in common, and we'll factor those out. So this gives the limit h approaches 0 of, well, if I factor that g of x plus h, then I'm left with fx plus h minus fx. And if I factor that fx, then I'm left with g of x plus h minus g of x, still all over h. Well, let's go ahead and split up the fraction. This is something we know we're allowed to do. When you've got one term and another term over top of h, we could put this one over h and this one over h. So that'll give the limit h approaches 0, g of x plus h, and then maybe I'll use square brackets here just to help distinguish the terms, over h, plus fx gx plus h minus g of x. And really I should throw some even bigger square brackets because it's all being limited. Now remember, the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits. If you look here, you could think of this as like a gx plus h times this portion, and here you have an fx times this portion. So we're going to use our limit laws to really break this up into each one of the individual limits. So we'll have limit h approaches 0 of g of x plus h times limit h approaches 0 of fx plus h minus fx over h plus limit h approaches 0 of fx times limit h approaches 0 gx plus h minus g of x over h. Well, we're pretty much done here, because if you notice, the first portion, because of that note we made initially, the h can plug in as 0 and we just get g of x. The next portion is technically the derivative of fx. Right? It's just the definition of the derivative. The limit as h approaches 0 of fx will just be fx. And then this is the derivative of gx. Well, usually we write it in a slightly different order because we usually write the derivative of f first. So we would write this as maybe the derivative of fx times gx plus fx times the derivative of gx, which is exactly what we wanted to prove. So we can put our box, and we've completed our proof. This is the wonderful proof of the product rule. So let's go ahead and make sure we have this rule down pat. Here are some challenge problems to ensure that we're using the product rule correctly. Go ahead and pause the video and give them a try. All right, so for the first one here, we have x squared plus 3x. The derivative of that will be 2x plus 3. And then we multiply by the other function plus 2x plus x squared plus 3x times 5x to the 4. All right, on the next one, we're going to need the fact that this is x to the 1/2. So we'll get 2.1 x to the 1.1 plus, well, 9 times 3, that'll be 27, x to the negative 4, times 5 e to the x minus 7 x to the 1/2 plus x to the 2.1 minus 9x to the negative 3 times 5 e to the x minus 7 times 1/2 x to the negative 1/2. All right, let's do one more here where we have, it looks like 3 functions, and then underneath is 4 functions. So pause the video and give each one of these a try. All right, so we can go ahead and do e to the x because the derivative is just e to the x, and then we leave the other 2 functions alone. Then we take the derivative of the next function. So we would get e to the x times 3x squared, and then 4x plus 7. Then we would take the derivative of the last function, which would be 4. If you want it written out, if you have 3 functions, f, g, h, you get f prime gh plus f g prime h plus f g h prime. You just do the derivative of each one at a time. So here we go. We've got one with 4 pieces, and we can go ahead and find the derivative. So we'll get 4x to the 3, and then everything else just gets written as it is. So it's a lot of writing for these questions, but the key is that we see how the rule works. Next up, x to the 4, e to the x is just e to the x, and then again rewriting everything else. Now, for questions that get so long that you sometimes can't fit them on your page, one thing you're welcome to do is put a plus, and then kind of snake an arrow along to keep going with the rest of it, just so it can stay on one page. Then we go for the next part, x to the 4 e to the x. Derivative of this will be 1/2 x to the negative half, x to the 5 plus 4x squared. And then x to the 4 e to the x, root x plus 1 times 5x to the 4 plus 8x. Now, for the next video, we're going to look at the division of functions, e to the x divided by x. And the question is, how is this going to work? Is it going to be simply e to the x because the derivative of e to the x is e to the x over 1 because the derivative of x is 1? Well, probably not, because it didn't seem like the derivative of a product was the product of the derivatives. That was not true. So we wouldn't think that the derivative of a quotient would be the quotient of the derivatives. But what would the rule be? And so I encourage you to go ahead and do the limit, right? You're going to set it up with e to the x plus h over x plus h minus e to the x over x all over h. I'm going to recommend that you do a little common denominator business here. Eventually simplify this dividing by h, put it as like a 1 over h, and go ahead and multiply in that fraction. Work it all out. Maybe use some special limits. Maybe use the fact that e is equal to 1 plus h to the 1 over h. Remember that. We have the limit h approaches 0 of 1 plus h to the 1 over h. Use all of the skills that we've been working on and just do your best. Work at it and see if you can come up with the derivative of e to the x over x. We'll go through the solution in the next video, but I encourage you, go ahead and give this one a try right now. See what you come up with. See if you can experience that discovery on your own. It's quite an enjoyable experience, and I really don't want you to be robbed of that by just clicking on the next video. Now for homework, you can take a look at the product and quotient rule worksheet. We obviously haven't learned a rule yet for quotients, so you can't do a bunch of them, but you should be able to do, it looks like maybe questions 1 through 8. You should be able to take a look at those and save the ones with quotients for once you learn about how to do the derivative of a quotient. So hopefully you enjoyed this video, and as always, thanks for watching.